Good morning. I'm David Rubenstein. It's my pleasure to chair session 4. And our first speaker is Nathan LeBrasseur from Rochester, and he's going to tell us about myostatin as a modulator of muscle mass, mobility, and metabolism.
Thank you very much. Good morning, everybody. It's really a pleasure to be here. Thank you, Aubrey, for the invitation and, more importantly, the free beer. So today, Aubrey asked me to talk a little bit about our work in the field of myostatin, and I think this is really an incredibly exciting area of investigation that holds a significant amount of promise for countering the profound loss of muscle mass that occurs with aging, and now this is commonly referred to as sarcopenia, and we're interested in both its functional implications of losing muscle mass in late life, but also the metabolic implications. And some of this work is not particularly new, so I apologize for that, but I want to give you a good overview of it. And then at the same time, I'd like to finish the talk with some discussion about potential future applications in the areas that we're heading. So this picture is really in part for dramatic effect. It's a slide that really exhibits the profound changes in skeletal muscle with the aging process. So as you can see in the lower CT scans, we reach peak muscle mass by our early 30s. And here you can see nice, robust quadricep muscle groups and hamstring muscle groups. But as we age, we not only lose the size of our muscles, but we see the incorporation of lipids both within and surrounding the skeletal muscle fibers. And this is the marbleized appearance that we see in our steaks when we put them on the grill, but it's not particularly good for skeletal muscle function or metabolism. And the fact that we start to lose muscle mass in very early life suggests that skeletal muscle aging is one of the earliest hallmarks of aging, and it's also one of the most profound. So when we look at the transition from our early 30s to, say, our 90s, we lose about 50% of our skeletal muscle mass with the aging process, and this is really quite profound. And again, I'll get more into the metabolic implications and the functional implications of this, but in particular, it's surprising and somewhat concerning that when we think about the primary causes of institutionalization in late life, which includes loss of function, poor medication compliance, and incontinence, 1 in 5 individuals over the age of 50 report difficulty in walking a quarter of a mile, climbing a flight of stairs, or lifting a 10-pound object. So early as 50 years of age, and this is more than coincidental with the age-related changes in muscle. By the time we reach our 80s, now nearly 60% of individuals have difficulty doing these very simple tasks that promote independence and promote healthy aging and independent living. And that's really why we are particularly concerned about age-related changes in skeletal muscle. So these functional limitations are concerning in and of themselves, but the real issue from the socio-medical perspective is that they're largely responsible for the high occurrence of falls in the elderly, again, institutionalization or loss of independence, and even death. So now people are talking about gait speed as actually the 6th vital sign. So those who walk less than 1 meter per second have higher incidence of death within 10 years, as well as a number of other adverse health outcomes. So with that introduction, my laboratory really focuses on skeletal muscle aging from 3 perspectives, with the big picture outcome of being these limitations in physical function, as well as metabolic implications of aging. And the way that we go about this is we do a cell-based program where we use kind of cell culture techniques to really think about the molecular mechanisms and biological underpinnings of aging skeletal muscle. And then we do a number of different models looking at skeletal muscle from an organ system, and then do some clinical research looking at kind of the big picture story about age-related changes in muscle. And over the years, we've really been looking at a number of different strategies, and these range from, again, different metabolic factors to growth factors to catabolic factors in muscle. But what's really captured our attention in the last 3 years is a story about myostatin. So myostatin is relatively new. It's a member of the TGF-β superfamily discovered in 1997 by the laboratory of Sejin Lee at Johns Hopkins University. And the phenotype of a myostatin deficient mouse is a double muscling. So you don't need to be a muscle biologist to understand what this picture implies, but you can see when we delete myostatin from a mouse, we get a doubling of skeletal muscle mass. So myostatin is a muscle-enriched negative regulator of muscle mass. It inhibits skeletal muscle growth and differentiation through a number of different cellular processes, and what this talk is going to be about is strategies to disrupt myostatin signaling. And it's not a story that's just unique to mice. Many of you are probably familiar with the Belgian blue cow. So there's different breeds of sheep, cattle, dogs that have naturally occurring mutations in the myostatin gene that lead to this hypermuscular phenotype. But what really captured my attention in my lab's interest in myostatin as a therapeutic target is this story. And there's really two kind of take-home messages here. So if you look at the left-hand column, this is a normal kind of wild-type whippet. There's 3 different dogs here. If you look at the far right column, this is the bully whippet. So this has a homozygous mutation in myostatin that drives a profound hypermuscular phenotype. The problem with that dog is that it's so muscle-bound, its function is actually impaired. It's too muscle-bound to run fast or even take care of itself. In the middle column, however, is a heterozygous mutation in the myostatin gene, which also leads to a hypermuscular phenotype. And when I talk about 2 kind of key take-home messages from the slide, number 1 is if we can reduce myostatin levels by 50%, we can have a profound effect on muscle mass, which is very achievable therapeutically. And secondly, this loss of myostatin drives a profound increase in function. So the whippet dog here can run at about 60 miles per hour. So, and this has really been a challenge in the field of muscle as we've been looking at different strategies to increase muscle mass. It's been difficult to get those to translate to improvements in function. So we don't want to increase muscle mass just to look good at the beach, but we need to translate to improve function and improve independence in late life. So that's why this therapeutic target has really captured our attention and our interest. And lastly, myostatin is highly, highly conserved. So even from fish to man, it's highly conserved. And in fact, there's now 2 reported cases in humans of naturally occurring mutations in the myostatin gene that lead to a hypermuscular phenotype. This is a picture of a newborn, and then at 7 months showing profound muscle mass increases. The parents allowed the child to be followed till about 4 years of age, where he showed just really remarkable feats of strength, if you will. And then because of just the public scrutiny, they no longer allow the child to be followed. But as far as we know, he's perfectly healthy. So the real question is that we have these naturally occurring mutations or forced genetic alterations in myostatin in animal models that lead to profound muscle growth. And part of these are developmental changes that lead to really hyperplasia and hypertrophy of skeletal muscle cells. So we have more muscle cells that are larger if we mutate myostatin. But what happens if we go into old animals at 24 months of age and we use a biological approach to disrupt myostatin signaling? So we developed a myostatin antibody and delivered it IP 1 time a week for 4 weeks and looked at the effects on old mice. We used exercise training as a parallel intervention just because of our interest in looking at big picture outcomes such as physical activity in mice as a surrogate for physical function. And we knew that exercise training induces nice changes in physical activity levels in mice, so we used that as a positive control. And then we also looked at how these 2 interventions combine and perhaps have synergistic effects. And what you can see here is nothing too dramatic in terms of body weight or changes in fat mass, but in the old mice, over the course of the intervention, probably in part due to just the stresses of the trial, in addition to the aging process, we see reductions in lean mass in the control mice, but we actually see a maintenance or an increase in lean mass in the myostatin antibody-treated mice. And this is not to make a big story about this, but the real story is that in a matter of 4 weeks, we caused about a 17% increase in the weights of individual muscles. So in the mouse, the liver is certainly a key contributor to lean mass weight, and we didn't affect other organs other than skeletal muscle. And this is just an example of the quadriceps, but we had a profound effect on all muscles examined. In terms of strength, the short-term intervention was not dramatic. These are strength changes relative to muscle weight or body weight, and what that suggests is that even though there's trends to improve here, when we normalize it to muscle mass, we might not be changing muscle quality. We're probably just changing muscle quantity. But in terms of fatigue, all 3 groups that were treated with either exercise, the myostatin antibody, or a combination showed improved fatigue resistance, and we'll get back to that a little bit later as well. In terms of measures of physical function that we think are clinically relevant, and we're trying to kind of develop more of these tests and measures to conduct in mice to help predict the ability for studies in man, when we look at running time or distance to exhaustion, even though exercise-trained mice are running on the treadmill every day, the real changes that we observed were actually in the combination group. So here you can see in the right-hand column in these graphs, in the black bars, is that mice that were receiving both exercise training along with the myostatin antibody, had the most profound changes in both running time and running distance to exhaustion. In addition, what we're pretty pleased to see is that, as we had hoped, is that exercise training not only increased habitual physical activity levels, but in the combination group, this too was observed. And I'm going to speed by this somewhat quickly, but this is very descriptive in this study. But just looking at some of the changes in cellular signaling activities, what we had hoped to see was that there was improved responsivity of growth pathways. And as much as in the aging field we like to suppress the IGF-1 signaling pathway, or the PI3 kinase signaling pathway, it's really important from the perspective of proteostasis and skeletal muscle to remain sensitivity of that pathway to pro-growth stimuli. So in fact, we showed that in response at baseline, as well as in response to growth factors, that we were actually able to improve the responsivity of both growth and signaling pathways to pro-growth stimuli, as well as suppressed catabolic signaling. And we also saw some interesting changes in pro-metabolic signaling, such as in PGC1 alpha, which is a master regulator of mitochondrial biogenesis and skeletal muscle. So just in terms of the story in aging and physical function and muscle mass, clearly short-term myostatin inhibition increased muscle mass in aged mice. In combination with the exercise training, we really saw the most pronounced effects on exercise time and distance to exhaustion and habitual physical activity levels. And as we go through the talk, again, we try to sell these as really clinically relevant measures of human function and performance. I'll come back to the signaling events in a little bit, but we're excited that myostatin inhibition may in fact be a viable intervention for functional decline and potentially frailty in late life. So some of our work more at the cell level, again, has to do with kind of the regulation of both growth and metabolic signaling pathways. And what's clear in skeletal muscle is that there's incredible redundancy between these different pathways. So the same signaling processes that drive glucose transport are heavily involved with both protein anabolism and protein synthesis, as well as suppressing catabolic processes in skeletal muscle. And really my thinking has shifted in the past couple of years, going from we either need to turn up protein synthesis in skeletal muscle to promote growth, or turn off catabolism to inhibit degradation. But now this kind of concept of proteostasis, I think, has really hit the field of skeletal muscle, where in aging, I think this production or synthesis of proteins that are dysfunctional because of age-related changes is really driving some of the functional decline that we're seeing. So we've been putting more attention into protein turnover as opposed to just protein synthetic pathways. But the point of this slide is that, again, by relieving the inhibition of some of the pathways involved in growth and promoting pro-growth pathways, we're also enabling the system to handle glucose in a much better fashion, as well as probably improving metabolic flexibility, or the ability of the system to transition from utilizing glucose as a primary fuel source to using lipids. And, we are unfortunately unable to use age C57 black 6 mice as a model of metabolic dysfunction, because in fact they're quite metabolically healthy in late life. So we use the Obi mouse here, and this is a fat, fluffy one if you haven't used Obi mice before. And we kind of did an interesting study here using the myostatin antibody, but instead of coupling it with exercise training, we used a endurance training mimetic, a PPAR delta agonist that induces mitochondrial biogenesis and increases genes involved in fatty acid oxidation. So here is a story about comparing the effects of myostatin inhibition to PPAR delta activation, again, alone and in combination, to see if the profound changes of increasing muscle mass actually have metabolic benefits. And here's just a quick look at the data in terms of the PPAR delta agonist. As we expected, Obi mice that were on the PPAR delta agonist for a course of 6 weeks gained significantly less muscle weight. This is about a 13% reduction. It doesn't look dramatic, but it's meaningful. They gained less fat mass, no real changes in lean mass in the PPAR delta agonist treated mice or the endurance training mimetic mice. And the reductions in fat mass accretion were really largely due to subcutaneous fat mass gains. In striking contrast, the Obi mice actually gained more weight when they were on the myostatin antibody. Really no differences in fat mass accretion, but the differences in changes in body weight were really attributed to what we expected, and that's an increase in lean mass through an increase in individual muscle weights. Again, no effect on fat mass. What's interesting is, though we're directly manipulating metabolic pathways in muscle through these different interventions, the effects of the individual interventions were actually highly conserved. And this actually surprised us to some extent. But here you can see that the beneficial effects on the PPAR delta agonist on body weight accretion, fat mass accretion, and subcutaneous fat mass gain were retained in the combination group, as well as the increase in lean mass induced by the myostatin antibody was also retained. So, as I mentioned, the increase in lean mass in the myostatin antibody-treated mice resulted from an increase in the weights of individual muscles. So here you can see that on figure A. The difference between developing mice with a lack of myostatin versus mature mice that you treat with a myostatin antibody is that we see an increase in the weights of all muscles, and this is due to skeletal muscle hypertrophy, not hyperplasia. And here you can just see a rightward shift in the distribution of the sizes of the individual muscle cells in the myostatin antibody-treated mice. In terms of mitochondrial enzyme activities, or key enzymes involved in fatty acid oxidation, the PPAR delta agonist has the most pronounced effects, as we expected. So in terms of metabolic gene expression, this data wasn't as impressive as we had hoped, but it appears that myostatin inhibition has a more pronounced effect on inducing gene changes in enzymes involved in glucose transport and oxidation, as opposed to the PPAR delta agonist that is more involved in fatty acid oxidation and utilization. And these changes are not dramatic, but again, a relatively short-term intervention that we constructed here. So we've really driven the phenotypes that we had hoped to with the drugs, and for the exercise advocates in the crowd, which I am one of, I use the word exercise mimetic very loosely. It's not that we think we're actually replicating the effects of exercise, but just mimicking certain aspects of it. But clearly with the myostatin antibody, we induce this resistance training phenotype as reflected by an increase in body weight, increase in lean mass, and increase in muscle mass. Whereas with the endurance training mimetic, or the PPAR delta agonist, we drove a decrease in body weight, a reduction in fat mass, and an increase in mitochondrial enzyme activity. And the question really that we wanted to answer in this project was, are the metabolic benefits similar between these two very distinct interventions that largely target skeletal muscle? And here you can see on the left really profound changes in fasting glucose levels and non-fasting glucose levels in response to both interventions. And in fact, when we combined the interventions, we dropped non-fasting glucose levels by nearly 300 milligrams per deciliter. So really profound changes for this intervention. Fasting glucose levels in all treated mice were below 126 milligrams per deciliter, which we typically use as an indicator of insulin resistance. And then in terms of glucose response to a bolus of, this is a glucose tolerance test here. You can see that the PPAR delta treated mice responded the best, but the myostatin antibody treated mice also had a significant improvement in glucose tolerance. So then we use the CLAMS metabolic system to look at effects on whole body metabolism. And here you can see as a result, probably of the induction of an increase in lean mass, we see elevated metabolic rates in the myostatin antibody-treated mice. So lean mass is the primary organ system involved in determining our basal metabolic rate. So that makes sense that we see an increase in kcals consumed in response to the treatment we induced. Again, we saw an increase in total activity in response to the myostatin antibody treatment. This probably has to do with increasing muscle strength in fat mice that probably aren't too happy to get up and move around. And surprisingly, again, the myostatin antibody had a positive effect on exercise time and distance to exhaustion. So again, consistent with our previous findings. So here, the take-home message is that despite these two distinct interventions having markedly different effects on body composition and skeletal muscle gene expression, as well as liver and adipose tissue gene expression, which because of time I didn't show you here, both had very positive effects on whole body metabolism. We think that the impact of myostatin inhibition on metabolism really has to do with increasing skeletal muscle mass, though we do see some changes in circulating levels of adiponectin, but this is resulting in improved glucose homeostasis and tolerance, an increase in resting energy expenditure, and again, we see positive effects on, again, clinically meaningful outcomes for the aging world, which include endurance and exercise capacity. So you know, this is published data and stuff that we've been working on for a while. But it's interesting, 1 in 4 individuals over the age of 65 has type 2 diabetes. That's if you're Caucasian. If you're of African descent, it's 1 in 3, and Hispanic descent is also 1 in 3. So, as these two kind of worlds of obesity and aging collide, interventions that can benefit both physical function as well as metabolism are certainly promising. I just want to take a couple of minutes to talk about directions that we're going in. This is not necessarily work of our group, but just shows that, when we think about the complications and consequences of aging, again, myostatin inhibition is a very muscle-based approach. It's predominantly or almost exclusively expressed in skeletal muscle. There is a small amount expressed in fat, though it's hardly detectable. And when we use an antibody-based approach to this, or look at myostatin-deficient animals, we see positive effects on a number of organ systems. So in fat cells, there's a recent report coming out that suggests that there's smaller adipocytes in high-fat fed mice who are treated with a myostatin inhibition strategy. And there's actually some browning of their adipose tissue, which, from my metabolic perspective, I'm not really sure what that means, but it suggests that their fat tissue is better at handling the fatty acids and storing the fatty acids and utilizing the fatty acids as it should, and prevents steatosis in both in skeletal muscle and liver. In terms of the heart, this is the most common question usually asked. What's the effect of myostatin inhibition on other muscles? And in the heart, it appears in 24-month-old myostatin mutant mice that there's actually reduced fibrosis and improved ejection fraction. So that's encouraging and positive news. In other models that have used myostatin deletion or mutation, there's reduced inflammation in the liver in response to high-fat feeding and reduced steatosis. In the vasculature, myostatin null mice who are crossed with LDL receptor knockout mice show reduced fibrosis. Oh, I just copy and pasted that, I'm sorry. That's reduced atherosclerosis and reduced inflammatory cytokines. Sorry about that. And then in terms of the bone world, it's not surprising because of the profound effects of muscle on bone, that there's increased bone mineral density and increased bone strength in response to myostatin inhibition. This is just kind of a conclusion slide here, and I'm not going to show you the data, but we're particularly interested in the clinical realm in frailty. And frailty is defined as an impaired capacity to respond to stress. It's poor resilience. And in aging individuals, we see this profound susceptibility to things like anesthesia, pneumonia, chemotherapy, radiation. There's a laundry list of things where the elderly are just not responding as positively as younger individuals. And frailty we can define as operationally through the work of Linda Freed and Jeremy Walston as poor strength, poor endurance, low activity, slow motor performance or poor gait speed, if you will, low physical activities and elevated cytokine profiles. And if you look at this, the core components of this are largely modifiable. And we think they can be modified through interventions that affect skeletal muscle. So the group is now actively involved in looking at how myostatin inhibition might have a positive effect on outcomes such as hip fracture or pneumonia using preclinical models in mice. So that's the direction that we're currently going. And lastly, this is just kind of a take-home message where we think that there's emerging evidence that positive effects on skeletal muscle health and function can have a profound effect on a number of disease conditions, as well as promoting healthy aging and independent living in the elderly, and largely having an effect on not just lifespan, but more importantly, health span in the elderly. So with that, I'll conclude and just thank the help of my previous labs. I just joined Mayo Clinic about a year ago and just starting to build a great team there. I'd also like to acknowledge the help of folks at Pfizer that have been providing the antibodies for a lot of the myostatin work, as well as my clinical colleagues at Boston University. So with that, I'm happy to take any questions.
I was just wondering, I didn't see any young mice controls in the earlier studies. You showed that there was great improvement in the older mice with your interventions. How does that compare to the state of a youthful mouse?
Sometimes it's hard to make healthy look healthier. So in young mice who don't have either impairments in either metabolism or physical function, we don't see dramatic changes in some of the outcomes that I mentioned. There are improvements in measures of muscle strength. So if you look at specific force or muscle strength in a young mouse in response to the myostatin inhibition, you do see positive effects.
How does the regeneration in the old mice compare to a youthful state, though?
It's a bit suppressed. So the problem in aging is that interventions that typically are very anabolic in young mice, or humans for that matter, exercise, IGF-1 interventions, growth hormone, God forbid, have profound and very robust anabolic effects in young species. Where in old species, they're clearly blunted or diminished. And this anabolic resistance is something that we're very interested in, and we just don't quite understand. Myostatin is a little bit suppressed as well. It doesn't seem to be as dramatic as IGF-1 signaling, and we think that has to do with some of the pathways that are activated or involved. But it's slightly diminished in an older mouse compared to a young mouse as well.
Hi. So, yeah, sorry. In your 2009 study, it certainly looked as if the mice that were given both the antibody and exercise didn't gain back quite as much lean mass and didn't have quite as good strength and function on a lot of parameters. Now, is that just because of the energy deficit from the exercise, or what's going on there?
So the in a 22-minute talk, it's tough to tie it all together, but exercise actually will suppress anabolic, or endurance exercise will actually suppress pro-growth pathways, surprisingly. So the effects on increases in lean mass are not as pronounced when we combine resistance exercise or the myostatin antibody with endurance exercise. This is probably a better discussion to have offline, but what we think is critically important is that when interventions are designed to promote muscle growth in the elderly, that is combined with an exercise-based intervention. And that makes sense, right? We want to improve recruitment and utilization of the muscle that we're building. I think a lot of studies that are just kind of promoting muscle growth interventions in the absence of exercise are really going to be futile efforts. And we put inserts into our drugs now for hypertension and hyperlipidemia that say best when combined with diet and exercise. I don't know what that means in the drug inserts, but I certainly hope that's the way of the future for these pro-growth interventions.
So, sort of along those lines, but as far as clinical translation of the myostatin inhibition, where do you see that going? Antibodies probably not the best approach. You had some other mechanisms for small molecules and such to inhibit that.
I actually think a biotherapeutic is the way to go in terms of an antibody-based approach. We can get away with once a week and potentially once a month dosing with the right linker regions manipulated. So there's been 2 trials. One is with an antibody-based approach, and that was in older muscular dystrophy patients. And the trial, in my personal opinion, wasn't particularly well designed. It did show some improvements in lean mass, but didn't go far enough to show any efficacy. Safety was fair. There was some skin rashes. Some of that had to do with the concentration of the antibody in the delivery. The second trial that was really more promising was a soluble decoy receptor for myostatin. And that's a really interesting approach, certainly much, much, much more horsepower. So if you give a myostatin knockout mouse the soluble decoy receptor for myostatin, you get an additional increase in muscle mass, suggesting that there's other ligands that signal through that path, through that receptor, that induce muscle hypertrophy. The problem, though, with that increased horsepower is I think you have increased risk. So now you're affecting a number of different organ systems. However, a company by the name of Acceleron went into a phase 1 study in postmenopausal women, gave 1 dose, and looked out to 60 days. And that 1 dose resulted in a 1 kilogram increase in lean mass and about a half a kilogram decrease in fat mass. That lasted out to 60 days, which is really interesting PK/PD issues because you've only given 1 dose and they're pursuing once a month dosing for it. But we'll see where that goes. They then went into a muscular dystrophy population, kind of a orphan disease indication in Canada, and that trial was just stopped because of some nosebleeds that were occurring in the patients. And I think some of these other ligands for ActR2B or the myostatin receptor might have significant effects on the vasculature that we need to be concerned about.
I'm sorry, there's tremendous interest, but we've got to move on. The next talk